All right, have I got everyone's homework? So any questions that we didn't get to last time on this homework?
Can you go over 6?
6. Oh, thank you. Can you remind me what it asks?
It's about the chip size or memory size.
Oh, Moore's Law.
Yeah.
Cool. Yeah, that's good stuff. I'll take off my index and mark here. So, who knows what Moore's Law is all about?
Every 2 years,
Yeah, so something about transistors and size and numbers and every 2 years. Basically. So Gordon Moore made this observation many decades ago that every roughly 18 to 24 months, it looked like the number of transistors we were putting on a chip was doubling. And it's called Moore's Law, but it's really Moore's observation. But it's actually become kind of the driving factor in Silicon Valley. The whole semiconductor industry is driven by a desire to stay on this curve of doubling roughly every 2 years. There's documents produced, technology roadmaps that basically lay out where the industry should be at certain points in time in order to stay on this Moore's curve. And it's one of these things that continually feels like we're getting to the limit of this doubling, where this will continue for another 5 or 6 years and that's it. We're going to break the curve at that point because there's no way we can double beyond this physical limit. And inevitably, very clever people find ways to get beyond these perceived limits. And so this thing has just persisted again and again and again. And people panic and say, what happens when we hit the end of Moore's Law? And one of my arguments for some time has been that Moore's Law is going to end not because we fail to double, but because we're going to be suddenly going up by like 100,000x every 2 years. We're going to actually break the curve in a very different direction. And that usually raises people's eyebrows. But I have reasons for saying that, besides raising eyebrows. So let's say Moore's Law holds. Transistors double every 2 years, assuming a quarter square inch chip has 1 billion transistors in 13. How many transistors will a half-inch square chip die have in 2020? So how do you go about answering this? What are the pieces we need?
First what I did is I went from the quarter-size chip to a half-size chip because that's what it was.
Okay.
It doubled.
So that'll double. If it's a half-inch square, that's twice the area. So instead of 1 billion transistors, 2 billion transistors. So 2013, 2 billion, 6.5 inch squared. And then where do you go?
After that, I found the difference in years.
Okay.
7 years.
7 years.
Yeah. And then, so what I did is I multiplied it by 3 times.
Okay. So 7 years, how many doublings is that? 2, 4, 6. It's going to be 3 doublings halfway between the 3rd and 4th doubling. So we could double this 3 times. And what we're really doing, we could make a little table if we wanted and just say 4 billion, 8 billion, 16 billion. 16 to 32 billion maybe, something like that. Doublings every 2 years is kind of a weird thing because it's not a smooth curve, right? It jumps. So what if it doubles every 18 months? So 2013, so let's do 2014 and a half. That's a year and a half later. 2016, 2017 and a half. 2019, and then 2020 and a half. Let's go for that. That's only 5 months later. So 2, 4, 8, 16, 32, 64 billion versus 16, both pretty impressive numbers. This is, I don't know what the die size is, but in terms of a large number of transistors, some of our programmable devices are running into several billion transistors right now. But I think that may be a bigger die than a half-inch. Cool. All right, so if you turned in your lab as of about an hour ago, I probably graded it already. If you turned it in more recently, I'll get to it later on. The labs look good, so that was a good warm-up exercise, lab one, a couple of experiments, getting into MP Lab, building a circuit. A couple of quick comments on the lab reports, and I put these in the comments also on your lab. When you get your grade, it's worth running through your lab report and looking for annotations. I'm not positive how they show up, if they're highlighted in some way or not, but I try to put them in red, although I think I forgot today. But I try to put them in red and their annotations in the document viewer. So a couple of recurring themes. One, disassembly listing, okay? You want to include the disassembly listing rather than just the source code. And you can actually copy and paste inside MP Lab. You can drag the mouse over and copy all the text in the disassembly listing and then paste that in. That's a little easier than doing screenshots, and it's also a little easier to read in some cases. Two, anytime that you put code into a report, change your font. You want a fixed space font instead of a proportional spaced font. Most fonts like this, an O takes a lot more space than an I, but your columns won't line up if you use that kind of font. So Courier or Courier New are sort of the standard fixed space fonts to use. That's just a nod to style, but it's good to know for future classes as well. Circuit diagrams, I want you drawing the circuit diagrams by hand, okay, rather than copy and pasting them from the report. The reason is I want you to get extra practice at looking at these circuits and understanding them. Wiring them up in the lab on a protoboard is one way to do that, but drawing them is also another way, okay, to reinforce how these things are connected and so on. I didn't take points off for these things this time, okay, these are just comments. The new experiment, you do not need to do that new experiment. You need to come up with a new experiment, describe it in sufficient detail so somebody could do it, and describe what the expected results are, the outcomes of the experiment. But you're not required to go in the lab and actually go through that experiment yourself. Okay, so if you want the student to do something like, you know, some really ambitious program, it doesn't mean you have to know how to do it. Okay, but presumably it's something that you think would be, you know, doable without too much beyond the course. So, new experiment, disassembly listings, draw circuits. I think that was it. All right, so we will talk about Lab 2 later. I want to get into more of MP Lab X and more of programming aspects of the PIC processor. So we're going to be starting to write programs, and for Lab 2 you're going to have to write a program to do some addition. It's our favorite 2-bit adder problem once again. This will end up being the easiest of all the 2-bit adders we've done, I suspect, because it's all going to be software, right? The hardware hookup is pretty simple. It's just switches and LEDs. All the good stuff's done in the program. So, somebody asked me in their lab report, and this is a really good question, how do you figure out which registers to use for what, right? So if you looked at the code for Lab 1, we had a variable called count. It was in location 80 hex. We had something called last. I think it was in location 81 hex or something like that. There's all these different variables in different memory locations. Where do you put those? And the shortest answer is it's really up to you. Okay, you're playing the job of the compiler. The compiler takes a program, converts it into assembly language. Since you're writing assembly language yourself, you are the compiler. And one of the things the compiler does is it goes through your program and it sees things like integer I, integer j, and it says, okay, I is an integer, it needs this much storage, I'm going to put it at this location in memory. And j I'm going to put over in that location in memory. And it keeps track of it, and when you want to read the value of j, the compiler says, oh yeah, I stored it over there, and it writes code to read from that location in memory. That's what you're doing. So usually one of the first things you're going to be doing as you're thinking about how to write an assembly language program is figuring out your memory map. Where do you want things stored? And this bank of general purpose registers, so location 0, 0 through FF, those are indistinguishable from each other. They're all general purpose, they're available for you to use for anything that you want. Typically, general purpose storage of variables, temporary storage, accumulators, counters, status, but it's up to you. So if you want to have 5 variables in your program, somewhere you're going to want to decide where you're going to store those, and you're going to want to write those down somewhere that you know. So maybe I'm going to put I at location 0, and j at location 1, and count at location 2, and flag at location 3, and sum at location 4. And I'm writing those down because every time I want to read the value of, say, sum, I need to know where did I store it. So I'll look at my little cheat sheet and I'll say that's in location 4. But we also have this directive that lets us say something like sum equals 4. And then if I want to add 1 to the sum, instead of saying increment file register 4, I can say increment file register sum. So once I know where I'm storing these variables, I can set up these EQU statements, and I can refer to those locations by name. But if I do the following, if I say flag equals 4, and sum equals 4, I've got 2 variables pointing to the same location. That's not what I want. Because when I do something to sum, I'm actually doing it to location 4, which is also where I think I'm storing this variable. So you really want to make sure when you set these things up, everything's got its own memory location. And if I wanted to work with something bigger than 8 bits, I might take 2 or more locations in a row and say these 16 bits from these 2 locations put together, that's what I'm going to treat as my variable x. And this would be the beginning of x, and this would be the end of x or something. So you've got to have some idea in your mind how you're organizing your general purpose registers for variables, but then set up some EQU statements and just use the names. All right, this brings us to the question of I/O. And we did some I/O in the first lab. But let's see how that works. Oh, the other announcement, I'm going to postpone the quiz until next Tuesday because I want to give you a chance to start on homework 2 and then ask questions about homework 2 on Thursday. Work on it over the weekend, convince yourself you're good, and then we'll have chapters 1 and 2 on the quiz. Because I want you to get quizzed on like coding instructions and binary and stuff. Yeah?
And do we get notes for the quizzes?
It's on Canvas. I think I said 1 page in notes. I don't remember if I said 1 or 2.
You didn't specify, you said for exams and tests.
Yeah, it's a test.
Okay, so.
Yeah. And you also get to use that blue sheet, that collection of pages from the data sheet. All right, so I made a comment last week that said in our memory, and this is data memory we're talking about, not program memory. So in our memory, we can read values, we can write values, we can increment values, decrement, we can do all these things. We can pull stuff out of here, modify it, write it back. And it said to do input and output to and from this chip, what we do is we have certain memory locations that are special and that are somehow connected to things other than just random storage. So these are the so-called special function registers. These are general purpose registers from 0 through 255 decimal, the first 256 locations. But there's also 128 or so of these special function registers. And if I write something to these, I'm not just writing a value into memory, I'm actually interacting with some piece of hardware. For example, and we're only going to look at the 18-pin version of this chip. That's the one we're dealing with. The 20 pins almost the same. So we'll look at this one. So there are some pins labeled RB0, RB1, RB2, 3, 4, 5, 6, and 7. And RB so I'm using this to mean RB7 followed by RB6, RB5, and so on. This is something we call port B. And port B is a special function register. It's a particular memory location that we can treat just like any other memory location. But if you look on your blue sheet, towards the back, there's a table of special function registers. See if you can find port B on there and tell me what number it is. I think it's F81. Is it 81?
Yeah.
Okay, thank you. So we have 256 general purpose registers up here in the beginning. And then we have these special function registers from F80 to FFF. And the trick or the secret that I disclosed to you last week is that this memory actually has 12 bits of address. 000 through 0FF up here and F80 through FFF down here. So the full address of something in our data memory is actually 12 bits. And we use that access bit to choose whether we want those first bits to be 0 or 1. All right, so right here, let me change this label down here. Right here, is the 8 bits associated with address F81. That's what we call port B. All right, here's how this works. So, there's the 8 bits for this one memory location. This bit is connected to pin 8. And this bit is connected to pin 9. And this 7th bit is connected to pin 13. And each of these 8 bits is connected to some pin on this chip. And the mapping is bit 0 is connected to the one labeled RB0, bit 1 is connected to RB1, bit 2 is connected to RB2, so it's that pin up there. And and so on. So think about what this means. If I write something into location F81, let's say I write 0, 0, 0, 0, 0, 0, 1, 1. So I write the number 3 into location F81. I'm basically writing 5 volts to this pin from inside the chip. And if I put a multimeter on this pin and I measure the voltage, it'll be 5 volts. And the same thing with this pin. But pins 3 through 7, if I read the voltage on those, it'll read 0 volts. And now if I write a new number that in binary looks like 10000011, all of a sudden the voltage on pin 13 goes up to 5 volts. If I have an LED hooked up to that pin, the LED just turned on. And now if I write this value, the LED just turned off. So this is our link between the software and the hardware. And it's all done through registers like this. All right, does that concept make sense before we go into the details? Yeah.
So it only looks at the most significant bit then?
Say again?
It only goes by the most significant bit as to what's going to turn on? So
No, so it's all 8 bits.
Okay.
So if I write a 1 in this position, 0, 1, 2, the pin labeled RB2, which is right here, that goes to 5 volts now.
Okay.
At the same time, RB0 and 1 go to 5 volts, and all these go to 0 volts.
Okay.
So that's going to be the first detail. We write all 8 of these at once, right? This whole set of 8 bits is connected to this set of 8 pins. And if I just want to write a 0 to this pin, I can't really do that, right? I can change this to a 0, but whatever value is in these other bits, that's the value for these other pins. These pins are tied together, right? They work as a unit of 8 bits. And we've got to be aware of that because there's no such thing as saying, I just want to work with 1 bit, right? I mean, we can make that happen, but this location, when we write anything to location F81, we're writing 8 bits. You always write 8 bits at a time. And whether we write 0s or 1s, those 8 pins will go to ground or 5 volts accordingly. So that's one detail we're going to need to be aware of. But it's not the most horrifying detail. The most horrifying detail is this business that this could be RB6 or a PGC or T1OSO or T13CK1 or P1C or KB12. And we've got to somehow tell it, what do we want to do with pin 12? Do we want it to actually come from bit 6 of port B, or do we want it to come from T1 oscillator output, or from KB input 2 or something else? Because these pins are shared, right? Again, there's only 18 pins, some are used for power and programming. They're mostly multi-purpose, and we've got to tell the system, do we want to use this for this or that or this other thing? The other issue is, this is also how we input data into the processor. If I read from this location F81, I can read the voltage level being applied to each of those pins. So if you ground out all of these pins labeled RB0, 1, 2 through 7, and you read the value of F81, you should read all zeros. And if this pin, I don't know, let's say this pin 4 is connected to a switch, and that that switch is closed, so you got a 0. If I open that switch up, so now there's 5 volts sitting on this pin, and I read from this location F81, this is what I'll read. I'll read all zeros except bit 4 will be a 1. And then if you flip that switch so it's closed and I read from this location again, no, I read zeros. So the two details here are the same. One, we've got to somehow tell it, are we doing output or input? Because if I'm reading from a switch and I've got this connected to ground, and then I try to write 5 volts to this pin, I probably got a short circuit going. And my chip will get unhappy. So we've got to differentiate input from output. The other thing is, if all I care about is the value of what's on pin 10, and I read from port B, I may not know what's in these other bits. They may not be connected to anything, they may be just floating. And all I care about is the value of this bit right here, but I might read this, I might read this. And in all three of these cases, what I want to do is notice that bit 4 is a 1. That tells me there's 4 volts on that pin, 5 volts on that pin. So I'm going to need some way to break these 8-bit things up into individual bits and look at just a single bit, or maybe a pair of bits. And that's what you're going to be doing in lab 2. You're going to be doing a 2-bit adder. One of your numbers is going to be coming in here, your other number is going to be coming in here. And you're going to need to be able to look at these 2 bits and ignore all the others. And you're going to need to look at these 2 bits and ignore all the others to get your 2 numbers. So we need to talk about some techniques for doing that. But let me talk about this assignment of pin functions first, because it's a little more mechanical and a little more straightforward once you get the hang of it. But if you don't get the hang of it, it's horrifying. So how are we going to tell the system whether we want to do digital output, or we want to talk to a serial port, or we want to do some other crazy thing? How are we going to tell the system if we want to do input versus output? And the answer to these kinds of questions is always going to be the same. We're going to use the special function registers. That's almost always going to be the top level answer. So there's a special function register called TRISB. TRIS is short for tri-state. You may or may not remember tri-state registers from 250. But the idea of a tri-state was it was a way to electrically disconnect something from elsewhere in the circuit to effectively cut the wire from one point to another, so that a gate is no longer putting out a high or a low, it's just floating. So TRISB is an 8-bit register, like all registers. And each bit means basically the same thing with a slight difference. So let's just look at this least significant bit. If this is equal to 0, then RB0 is an output. All right, RB0 is pin H. If this is equal to 1, then RB0 is an input. So TRISB lets us specify bit by bit whether each of these RB bits is an input or an output. And we can mix and match. We could have RB0 and 1 be inputs and RB2 and 3 be outputs if we wanted. And how would we do that? Input, input, output, output. And if we don't care about RB4 through 7, it doesn't matter what we put in those 4-bit positions. All right, this is in some ways a pretty straightforward concept, but it's a source of a lot of confusion. It's something you have to do again and again. Every time you work with this chip in any of these labs, first thing you're going to have to do is set up your input and output. You're going to see it on homework, you're going to see it on quizzes, you're going to see it on exams. So it's an important concept, but it's also really typical of the kinds of things we're going to do with these SFRs. We're going to usually break them up into particular bits, and each bit's going to mean something. Right? This bit tells the system whether RB3 is an input or an output. That making sense? So here's an exercise. If you want to read from pin 17 and write to pin 18, what should TRISA be set to? So you want to read from pin 17, do something presumably, and then write to pin 18. So how do we go about answering something like that? So what is pin 17? RB2. So we want to read from RB2. And what is pin 18? RB3. So we want to write to RB3. And TRISB, each bit tells us whether the corresponding RB is an input or an output. So if we want to read from RB2, what bit do I need to set in here? I need to deal with this bit right here, bit 2, and since I want it to be an input, I need to make that a 1. And if I want to write to RB3, I need that to be an output. So what bit do I have to set in here for RB3? 0, where does it go? Yeah, the 4th position, right here. And I don't really care about those other positions, so I could put anything in there I want. I could roll dice or flip a coin or something and decide what to put in there. But in practice, if you don't know what a pin is being used for, what do you think is safer, setting it up as an input or an output? Probably an output. Why?
If you set it as an input, you could damage something.
It's actually the other way around.
Yeah, that's what I meant. The
Yeah.
other way around.
So suppose that somebody's using this to connect to a switch, and they've got this input connected to ground, or this pin connected to ground. If you set it up as an output, you're going to be writing a value to it. It might be a 0, it might be a 1, but you'll be writing something, and you could potentially have a short. If you set it up as an input, and they're using it as an input, no problem. The other way around, if they're intending it to be an output, they've got an LED hooked up to it, and you accidentally set it up as an input, there's no harm done. You're reading the value from an LED, you might get a 0, might get a 1, it's meaningless, but it's harmless. So there's this notion of a do no harm state, and for general input outputs, usually setting something as an input would be safer. Now if you're building the circuit, you've got complete control over it, you know you're not hooking anything up to those pins, really doesn't matter. Flip a coin, put in zeros, whatever you like. So these can be whatever. But the most professional approach probably would be to put ones in there to make them inputs. But the important part is these 2 bits. Yeah?
I'm not real clear on how we're knowing how to map that. So knowing that position 2 is for RB2 or RB3?
2.
Okay, so how do we map that? How do we know which is for which?
From here to RB,
Yeah, to know which, to know the RB2 is that position and RB3 is the other position.
so this is always RB0, 1, 2, 3, 4, 5, 6, 7.
Okay,
It's just
so it's
straight
just the
linear
constant.
ordering. Yep,
all of them, okay.
yeah. All right, so we make all these 0 if we want to simplify our arithmetic. We just load the value x4 into TRISA, and we've got our pins set up the way we want. 0, 4, same as decimal 4. All right, so you'll do this constantly again and again and again. In addition to port B, there's also port A, which is RA3, RA2, RA4, RA1, RA0. We don't have the full bank of RAs available. They only go up to 4 and sometimes RA5, but you have to do special stuff to use RA5. But if you want to use the pins that are labeled RA something, you do port A instead of port B to actually write to or read from, and you use TRISA A instead of TRISA B to control the direction. So we've got 4 new SFRs now, port A, port B, TRISA A, and TRISA B. And the A's and B's work identical to each other. All right, there's one other SFR we need to deal with to do I/O. Oh, no, that's right, that's all of them. So these pins that I've underlined, this first one is labeled RA0/AM0. This is RA1/AM1, RA2/AM2. This one's RB0/AN4. The part I'm interested in is these ANs. AN is short for analog. So in a few weeks, we'll talk about another piece of the PIC, which is an analog to digital converter. You can take an analog voltage, something between 0 and 5 volts, and feed it into one of these pins labeled AN, and ask the system to tell you what that voltage is, and it'll measure it for you, and it'll convert it into a binary number. So if you have something like a volume knob that changes smoothly between 0 volts and 5 volts, you can read exactly what the voltage is. Well, not exactly, but you can read the voltage within the precision of the converter. So it lets you take analog values in from the outside world, which is really useful. But again, we're multiplexing pins. There's 7 analog channels. I thought there were only 6. But there's 7 analog channels we can feed things in on, AN0 through AN6. But they use the same pins as some of the port A or port B values. So we need to tell the system, are we doing digital I/O or are we doing analog reading? So there's another SFR called ADCON1. I haven't memorized its location, but it's somewhere in that bank of special function registers. And here's what this looks like. So this first position here, bit 0, controls whether we want to use AN0 or not. If you put a 0 in here, we're trying to read an analog voltage on pin AN0. If we put a 1, we're not trying to read an analog voltage, it means we're going to do digital input and output. This next bit, this controls channel AN1 and so on. This 6th bit controls AN6, and the 7th bit is unused. So if we wanted to put an analog signal into this pin right here, pin 6, we would say, okay, an analog signal here is going to be AN2, that's the channel it's coming in on. We would want to set position 2 to be a 0. We don't have to worry about this for a few weeks because we're only going to do digital input and output for now, which means we don't want to use any of these AN inputs. So for now, we're going to set ADCON1 to be all 1s. And we don't care what goes in this 8th bit. If we wanted to put a 0 in there, this would be hex F. If we want to put a 1 in there, it's hex FF. Most of the code you'll see puts a 7F into ADCON1. We're putting a 0 in here, it doesn't matter. But usually if you don't care about a bit value, we set it to a 0. All right, so let's summarize. If you want to do digital input or output, you've got to set up the ADCON1 register. And there's no reason not to just always set that to 7F. Beginning of your program, put 7F into that register, right? Until we get to the part where we're actually doing analog stuff. So you got to set ADCON1 to 7F. You got to figure out what value you need for TRISA and or TRISB and set those values up. And then you either read from or write to port A and or port B to actually do the output or the input. And you were doing all of that in your first lab. So here's where we put a 7F into ADCON1. Here's where we cleared TRISB and we loaded the value 1 into TRISA. So TRISA got the value all 0s followed by a 1. Which means RA7 through RA1 were all 0s and RA0 was a 1. So what does 1 mean for TRIS? Input or output? Memory test. Input. So this code set port A pin 0 as an input. That's exactly how it's working. The way I remember this, that's a 1, that's a 0. I only worked with this for like 2 years before I noticed that. All right, so you set up ADCON1, you set up TRISB. TRISB is all outputs, TRISA is all outputs except for bit 0. Most people like to clear port A and port B. I don't think it's necessary. I've never found a reason for it. I never do it, but it's actually in some of the documentation. that you should do this, but I've never seen an explanation for why. It's a superstition thing, I think. It does no harm, and most of the code you see will have those clears in the beginning, but I think it's probably a remnant from some past experience. All right, so that's lots of detail on doing inputs and outputs and working with SFRs. And again, every time we work with special function registers, it's the same idea. Usually there's some set of bits, maybe one bit, maybe a few bits that we need to interact with, and we'll do something accordingly to control some piece of the system. All right, let's do a 5-minute break, and then I want to get into some coding techniques for actually doing things that we'll need to do for lab 2.